Okay, hello everybody. I am Francesc from the Blosc development team. I am also the CEO of ironArray, which is a nascent library for performing computations on top of compressed data. And today I am going to talk about HDF5 and Blosc2, and especially how to unleash the full potential of Blosc2 from HDF5. So first of all, let me introduce the Blosc development team. Without them, we couldn't do all the strides that we did in the few last years for producing Blosc2. So thanks to all them. And also a few words about ironArray. So ironArray it's a library for doing compression and also computation on top of that. And the idea is to bring the data in compressed state into the CPU caches, in private CPU caches, do the compression inside of the CPU caches, do the computation step there, and then compress again and before writing again or storing again in storage. And the idea is to reduce the pressure on top of the bus memory or buses disk. And in general, that is good for improving performance. Okay, so after this shameless plug, let me go back to what is Blosc. So Blosc, it's all around sending data from CPU to memory faster than CPY. This is the goal. And it works by splitting the data in blocks for better cache use in the typical divide and conquer approach. And it can use different filters like shuffle, bit shuffle, and different codecs like LZ4, ZLibs, the standard, whatever. So that's the introduction of Blosc. Then regarding the origins, by 2009, it was very clear that compression was slowing down storage in PyTables and HDF5 a lot. So work began towards producing Blosc, and 1 year later, Blosc 1.0 was ready for productions. And among its innovations was there was a shuffle filter that was optimized for SSE2 and Intel CPUs, which is much faster, and then also multi-threaded operation. And then last year we released the Blosc2 with lots of new features I am going to describe now. Also, so what are the advantages or the new features of Blosc2? So Blosc2 is the next generation of Blosc1. It comes with sorry, I see some noise. I don't know if it is my. Okay, thank you. I think it's nice now. It comes with 63-bit frames that expands over the existing 31-bit chunks in Blosc2. So in yellow, you see the typical Blosc1 chunks, and these are complemented with one header of meta layers and one trailer with user meta information that can be added there, which is variable length. Okay, so this is an innovation. And also, let me show you an example of the decompression speed that we are claiming that it accelerates computations. So this is a Basemark based on actual data. It's precipitation data. It's been summed against some axis. It's a multidimensional data set. And we see that when we throw enough threads at the task, we can reach a point where data with computations combined with compression can be faster than computations without any compression at all. So without any compression, it's the blue bars. And we have different codecs here. For example, exceeding 14 threads in this machine, we can see that we can get better performance than using non-compressed data. This is one of the examples of applications that we are after. Well, as you know, all of you, HDF5 is all about multi-dimensions and chunking. So data can be stored in hypercubes and making retrieval very convenient. But there is a price to pay for this flexibility, and HDF5 is known to be slow when writing and retrieving hyperslabs of data. And this is well known by the HDF group, and in fact, they provided some years ago a way to bypass the powerful, although slow, chunk handling machinery in HDF5. And the result is that we can bypass all this pipeline for handling the chunks. We can get much faster speed. Okay. In general, they claim 10x for writing, which is a lot, 10 times faster. So this is our first proposal. So we propose to use Blosc2 inside of direct chunk machinery of HDF5. So here we have the proposal is to have an application, and we have here the chunk that we want to compress. The idea is that HDF5 just send to Blosc2 the chunk to compress, and then once it is compressed, H5D write chunk is in charge of writing the data in the storage in HDF5 files. Okay, and then once the data is there, if we want to read it, we can ask Blosc or HDF5 or the application can ask Blosc to read the data that is stored in the HDF5 file, and it can do that. Blosc2 can do that in parallel, doing parallel I/O, input-output, and also can decompress as well in parallel. Okay, so all the compression and decompression executes in parallel. Okay, and HDF5 is just responsible to read and to write data and to get and to tell Blosc2 where to find the data, which is the offset of the chunk of the compressed chunk in the storage in the HDF5 file. Okay, so the consequence of this proposal is that HDF5 will be able to use all the Blosc2 advantages. Let me show you some of the most important ones. So, for example, Blosc2 is fine-tuned for cache usage. So whenever we have to compress things, the data or the chunk is split in what we call blocks. Okay, so we have different threads, and all these blocks are executed to the pre-filter, the filters pipeline, and then the final step is the compression via the codec. And it is stored either on disk or in memory. Okay, but the one important thing is buffers are reused inside CPU caches. So that means that a lot of speed can be gained. And then another advantage is that we can leverage I/O parallelism. Okay, when we have the data which is on disk, which is split in blocks, Blosc2 can read in parallel as well. Okay, so it can read the different blocks and decompress in a parallel way, also making use of the minimal amount of memory as possible. And that means that parallel I/O can be effectively achieved as well. Also, Blosc2 comes with Caterva, which is a library that allows Blosc2 to go multidimensional. So Caterva provides a meta layer representing the multidimensional thing. And for example, if we have here the array, we can see that the array can be split in chunks. This is typical in most of the chunk containers like HDF5 or ZAR or whatever. But the innovation here is that Caterva allows a second partitioning. So each chunk can be also partitioned in blocks, okay? And these blocks can also be multidimensional, and that has a lot of implications as well. This is, we are going to get there. So the benefits of this Caterva layer is that we can get improved compression ratio because data is packed in a way that can show higher spatial locality. So that could benefit, for example, this ZFP, which is a codec that has been registered recently inside of Blosc2. And also, by using the Caterva layer, we get improved hyperspad. We can get improved hyperslab query speed. because only the blocks that are interesting for the user can be read and not the others. So let me explain a little bit what's this selectivity it's about. So on the left side, we see the typical HDF5 container. And let's suppose that we want a thin slice in the middle of the hypercube. In that case, we are enforced to read the whole chunks that are part of the interesting data, so to say. Whereas if we have an additional partition level, as allow Caterva and Blosc2, we can read only part of the data, okay? Not the whole chunk, but only the affected blocks. And that means much more selective and hence faster queries. This is the approach that take Caterva and also ironArray. Here we can see the slicing performance on disk, okay, of one array. We're comparing ironArray, which is using already Blosc2 behind the scenes, ZAR, HDF5, and also TileDB. And we can notice that we can get better performance in general when using Blosc2, except for the dimensions where retrieving a chunk is already optimal. In this case, this dimension 1 means that Blosc2 doesn't have any advantage because the whole chunk needs to be retrieved, but still the overhead is not that bad. But for the other dimensions that are not optimized for the chunking, we can see that Blosc2 can get better performance than ZAR, for example, and much better than ZAR, than HDF5. So you can see this Basemark here in this URL. So yeah, Blosc2 can bring parallelism and efficiency. In this plot, we can see 3 compressed arrays that are decompressed, operated with. We are computing the mean of these 3 arrays, and then the result is compressed again. We are using ironArray, ZAR, and HDF5. We see that HDF5 is taking the longest time, probably because of this special handling of chunking. ZAR can do much better, and ironArray it's not only faster but also computes or consumes much less memory, which is a nice thing when you are trying to handle very large data sets. And then, yeah, let me show you some quick Basemark that we recently did by using a specific Basemark on Blosc2 plus HDF5 direct chunk. And we used ERA5 data set with data which comes with wind, speed, air, temperature, solar radiation, snow, many different things. And we can see that when we use Blosc2 plus setflip as part of plus HDF5 direct chunk, we can see that we can get between 10x and 20x faster speeds for writing, and 20 to 30 times faster for reading. Okay, this is very preliminary because we just did the Basemarks, finished the Basemarks early this morning. But I think the measurements make sense, and I think they agree with what the HDF5 group also tested on for the direct chunk writes, at least. Okay. Also, let me show you briefly a second proposal in that we can provide, the Blosc team can provide help in determining the optimal completion pipelines. Especially because we would like to help people or teams to start using the most useful codecs and the filters as well. So for that, we are producing specific versions of Btune, which is a machine learning tool for selecting the best pipeline candidate on a chunk by chunk basis that adapts to the needs of the user. So this is how it works. This is the Btune state diagram. It comes with some states. And in different states, Btune, it changes automatically the codec and filters for different chunks, and it produces a score. Okay, then once a combination it's found that is good for this data set, then it passes to the next stage, which is changes the shuffle size. Also the number of threads are checked. So in the end, we can produce a combination of codecs and filters and a number of threads that works optimally. Okay? And this is active during the compression pipeline. So it automatically learns on the best parameters on the go. That's the important thing. We have a demo, also an interactive demo, but I don't have any time. If you are interested on that, in the question section, we can have a look at it. And we are also currently improving working on improving Btune, because one of the limitations that currently it has Btune is that it needs some warm-up tests just to come with a sensible guess for the combinations, right combinations of tests and filters. And we are planning to shorten this warm-up period by using deep learning techniques. And the idea is to come with some predictor for the entropy for every chunk and train a neural network on different data sets. And this will be used for reaching the sensible guess faster. Let me show you some examples of how it works right now. This is very preliminary, but we are getting already nice results, I would say. So in blue, we see the entropy detector, the entropy probe. We call it entropy probe. And then we have two codecs, which is Blosc LZ and LZ4, which has very similar properties. They are fast and they don't compress too much. And we can see that the accuracy after the training is not that much. Okay, it's just 60% of the times it comes with the right prediction. But this is quite normal because in the end doesn't matter too much which one is chosen because they have very similar properties. So they don't have very good predictions. However, when the codecs to be distinguished have much different features, like for example in this case Blosc LZ in red, and in green we have Z standard in this case. Z standard is much slower, but it compresses much more than Blosc LZ, right? And in this case, the neural network is the accuracy of the neural network. It's much more closer to 1, which is the expected thing. So yeah, even if it is preliminary, we are having like interesting results that we plan to introduce very soon in Btune. Okay, so as a conclusion, let me say that Blosc2 helps saving resources. Blosc2 is not a codec in itself. It's really should be seen as an orchestrator for a rich set of codecs and filters that allow CPU parallelization via multi-threading. It allows also the reuse and sharing of internal buffers for optimal memory consumption, parallel I/O, and it allows also more selective hyperslabs. And the result is a highly efficient tool for compressing and accessing your data your way. So the summary of proposals is that first one, it's use Blosc2 in combination with HDF5, the direct chunking mechanism, for efficient compression and parallel I/O, and also help in determining optimal compression pipelines by adapting to the user data and using machine learning techniques. As I said, the Blosc development team will be glad to be involved in efforts towards these goals. So finally, let me thank the donors and contractors as well. So without them, we could not have possibly put Blosc2 into production status. That came just 1 year ago, in June 2021. We are now at version 2.1, which is recommended for production. And as I would like to say in the Python development team, enjoy data. Okay, thank you for your attention. I will be happy to take any question if you have.
Thank you, Francesc. Let's see if there is some question in the chat first. No.
I have a question. I was wondering if you compared direct chunk reads and writes versus memory mapping. So
No.
Go ahead.
No. We haven't tested memory mapping because, well, yeah. What you are suggesting exactly?
Well, I think one way I've used the HDF library is just to get the offsets of the data. So one thing that if I didn't necessarily want my chunks to be compact, is I could ask HDF5 library to allocate the space early, get all the offsets, and then memory map the file and then interact with the file space via memory map, and that might provide a multi-threaded access. But there might be spaces between the chunks. I'm just kind of curious if that might actually provide performance advantage for something like Blosc, rather than trying to use the direct chunk read or write interface.
So you mean that different chunks could be memory mapped, so to say, and then have like an index for every chunk, right, in memory? Is that correct?
Yes, essentially.
Okay. Yeah, it's a good idea. It's a good idea. What I mean, our vision here is to try to be as compatible as possible with HDF5. As we learned about this direct chunk mechanism, I think we were like very curious about the kind of speed ups that could be achieved, and yeah, we are quite happy or very happy because essentially you are bypassing all the chunking handling mechanism inside of HDF5. So I would say that this is already a very good, so almost optimal approach for doing I/O. But yeah, doing memory mapping could be also another. I don't know if memory mapping would be compatible with HDF5 itself. What's your take on that?
I believe H5Pi and also the Julia package provides a mechanism to map contiguous data sets.
Contiguous. Oh, okay.
I think there is an API to get the chunk info, which would provide the address for each chunk if it's been allocated already. But I think that's the kind of the struggles. How do you deal with chunks that haven't been allocated yet, but you're compressing them in parallel? And so this is what maybe direct chunk write allows for.
Yeah, I would say that in our experience, the direct chunk approach is very efficient. So I don't think we can get much more speed than it's allowing this approach. But yeah, it would be worth to do an exercise on memory mapping.
You can hear me?
Yeah.
Francis, I had two questions. One was a naive one, is if you compress the data directly with a filter, HDF5 filter like Retrieval, and then you also compress it with a Blosc using the same filter, are the two files identical? Can they be read by both libraries, or you understand what I mean? Yeah. Will the Blosc using the same filter in Blosc look exactly the same?
You mean the bit shuffle which is the external project, external to Blosc, right? Not the one that is included.
Yes. So what if you use the same filter but outside of Blosc and inside Blosc?
No. It's different. It's different because Blosc adds its own headers, right, to the chunks, to the compressed chunks. So they are not bit by bit compatible. Although I mean, Blosc also comes with bit shuffle, so we can get exactly the same performance capabilities of the bit shuffle project inside Blosc.
Okay, and the second question is, how would you help people? One of the big worries of scientists is they can't read the data in 10 years' time if they use one of the filters which they don't know if this is still around. Has Blosc got any vision or suggestion how this can be managed to guarantee you can read the data in 10, 30, 50 years' time?
Yes. So Blosc2 has a policy, or Blosc has a policy to be always backward compatible. So for example, Blosc2 is backward compatible with Blosc1, right? So all the data that has been compressed with Blosc1 can be read in Blosc2. And the idea is to always respect this backward compatible with the future versions as well. Unfortunately, we are not providing forward compatibility because Blosc2 has much more enhanced capabilities, and providing forward compatibility can be a nightmare. But if planned carefully, you can start introducing Blosc2 in your pipelines, for example, and be sure that with Blosc2 you can still read the data that has been compressed with Blosc1. And that provides this backward compatibility. I think we will ensure that for the time to come. At least for sure for the Blosc2 branch or version, so to say. I mean, Blosc1 has been in production for more than 10 years now, and probably Blosc2 will have probably a larger time span, larger than 10 or 20 years, probably approaching 20. But it's difficult to say, right? It's always difficult. But of course, for this, yeah, we need some committees and some ways to ensure that backward compatibility will be respected. But I mean, our team is fully engaged or fully compromised with this thing, with compatibility issues.
Francesc, would a Blosc2 HDF plugin maybe needed a unique filter ID separate from the Blosc1 filter?
Yes, it will need a different one because yes, it's backward compatible, but it's not forward compatible, right? So you need another ID for that. Make sense?
Okay, so we have a question from Jiri.
Yes, this is Jiri speaking. So actually, if I understood it correctly, this whole parallelism is multi-threading, right? So do you have a way in mind how to scale this really for like HPC with a true parallel file system where you need to really distribute also processes across the nodes?
No, I don't have experience with parallel file systems. So typically we always do experiments with local file systems, especially with modern SSDs. And modern SSDs has repeatedly shown that when you do I/O in parallel, when you have different threads accessing different parts of the file, you can get faster speed than if you access the data in a sequential way. But unfortunately, we don't have experience with parallel file systems, which would be interesting to gain this experience. But anyway.